Hi, everyone. I'm Henrik. I'm the creator of Futureverse, a framework for parallel and distributed processing in R. When I first started out more than 10 years ago, I had this dream that I could share my idle computer, my laptops, and my office computers with friends and colleagues. And today, I'm very excited to say that we can do that. I have a working prototype called future.p2p. It's peer-to-peer compute clusters in R. Anyone can use it. It's super easy. So some of you already know Futureverse. And if you do not know, I will give you an introduction here. And for those who already know, I might recalibrate your understanding how it works. So follow me here, please. So the way you use futures, you load a package, library futures, and then you say what plan you want to do, plan multi-session. That means parallelize in your local computer. And then we have different functions that allows you to parallelize. So if you like per and the map function there's the fur package and the future map function that works the same, but it parallelizes those concepts and therefore run faster. And with this new package now, future.p2p, we can now do the same thing, same code, but now we can harness friends' idle compute powers and friends across the world. Okay, so let's step back here. What is a future? So futures were invented mid-70s, so it's nothing new. So if you look at R, when you do y assign the slow sum of a vector 1 to 10, what R does conceptually, it takes that right-hand side and looks at it. Okay, there's a function slow sum, there's data. I put that in a box. I pass it to the internal engine, and I run it. And this function takes a minute to run on this data, so it's slow. And when it's done, it puts the results back into the box, 55. And eventually, it gets back to us and assigned to the variable y. Okay. With futures gives you control of that step, those steps. So we can use that with a code. We can say now the right-hand side, we wrap that in a called future, we can handle to that. That's basically creating a box. And same way, we create a box and it sends it off to R and it processes still 1 minute. And then we have the concept of asking that box, is there a result yet? And eventually we get the Y55 back. So we split it up one step into two. Okay. So why is that useful? So imagine now we're doing this 3 times. We call the same function 3 times. It will take 1 minute each, so we know it will take 3 minutes to complete these steps. And what R does, it creates a box, process it, get the result, assign it, next box, and next box. So 3 minutes total. With futures, what's important to know here, the boxes are very cheap to create. It's the processing what's inside the box that takes time. So with futures, we can create the 3 boxes basically instantly. So we do that. And what Future Framework does, it will send it off to 3 parallel workers that runs now. Although each of them takes 1 minute, they do it at the same time, so we only have to wait 1 minute. And then they put the results back in the boxes, and eventually we get those results back when we ask for the value. Okay. This is all implemented in the future package. We've seen the future function to create a box. We've seen the value function to ask, look into the box and get the result. And there's another one saying, are you already done, resolved? But these are building blocks for parallel processing, and with that, you can build much more powerful things. I do not expect any of you to use these functions. You can, but most of you will use wrapper functions around this that hides these details. Okay, so if you consider the classical lapply function in base R or the map function in per, what they do, they iterate over some input data and call a function over and over. So you can think about them, they're functions that package things up in boxes and sending them to R, and they do them one by one, sequential. Okay. There are very fast futurized versions of those that works exactly the same, but it's packing it up in boxes, but it sends those boxes out to parallel workers and then collects the values back. Otherwise, they work the same. So from the outside, you can treat them as the same. Okay. So that's the power of futures. We haven't talked about this, but you also have the option to choose how to parallelize. Already today, you have 3 different ways to parallelize on the current machine. We have the multi-session, there are actually others that comes with the package. There's a future.caller package. There's the future.mirai package. We use the Mirai framework to parallelize. They will not evaluate the boxes faster, but they have different ways of shuffling around the boxes, okay? So there are pros and cons, you can read about them. If you have access to multiple machines in your office, at home, at the university, in the cloud, you can already now just point those and use those. And if you have an HPC, high performance compute cluster, you can use that, for instance, the Slurm job scheduler and harness the whole compute cluster and the power for that. Just one change of plan. And today, now you can also do it with your friends. You can send those boxes to your friends' computers, which I will show you. Peer-to-peer computing. So excited about this. Peer-to-peer clusters has two components. It has a message board. That's where you interact. Say, I have a box. Someone want to work with this. And someone say, I'm willing to work. Is there anything for me to do? That's very lightweight. You're only putting up post-it notes on board. So there's not much compute. It's cheap, fast. When there is like a client and worker agreeing, the client can send a box to the worker. And that's for peer-to-peer file transfer protocols. And the same protocols is when the results are sent back using that too. And the reason why we use that is like there's no need to set up a centralized and run a server where you transfer data. These boxes are just sent for well-established peer-to-peer protocols that just magically finds their way on the internet. Okay, so how do you get started? It's super easy. You create a Pico SH account. If you're watching right now, you can just do SSH pico.sh and you get an account. It's very private. All they ask you for username, no email addresses. They know nothing about you, okay? Then you can try it out by running a personal peer-to-peer cluster. That means you don't have to invite friends. And you can find instructions and examples online in the package vignettes. So after you have this, you're ready to share with friends. So imagine now Alice, Bob, and Carol has went through those steps. And Alice will let Bob and Carol say, hey, I'm willing to host this message board, Alice/friends, and I will invite you, Bob and Carol. No one else can access it. And then Bob is super excited. They will say, okay, I use plan, future.peer-to-peer, ::cluster, and connecting to Alice/friends. And they do. They get access to the message board. And then they run the future map and start doing compute. What happens there is they're creating boxes and they're putting them on the message board, but there are no workers. So no boxes are sent anywhere, nothing is processed. So we need workers, and it's very easy to contribute workers too. So here is an example of 6 workers. Alice contribute 2, Bob 1, and Carol 3, because Carol had a bigger computer. And it's a function call in R, and you just specify the name of the message board. And after this, there are 6 workers willing to work. So Bob's process will now finish. It's super exciting because the same code will now go out on the internet. The boxes will be sent that way. If you run it locally, the boxes will be sent to parallel workers running a local computer. The same code, otherwise. Pros and cons. With a peer-to-peer cluster, there's no limitation in number of users and workers that can join. So you can think of it, you can technically have huge throughput. You can process lots of boxes at any time. And you can imagine a public peer-to-peer cluster with thousands of workers. Okay, let me get back to that public one. The downside is high latency because the boxes has to be sent, and peer-to-peer file transfers are not super fast. It takes time for them to find their way. So we're saying a very, very simple compute 1 + 2 can still take 1 to 10 seconds because sending the box over and returning the results comes with overhead. It's nowhere optimized yet there, so things will be improving, but we're talking seconds, the round trip. Okay. So if you do things that are 30 seconds or a minute longer, then it's worth doing this. If you do other things, you probably want to parallelize locally. Let's talk about public peer-to-peer, because I make that very hard to do right now because there's a big risk right now. Right now, you have to do have mutual trust in your friends, because either someone could, on purpose, with malicious intent, have code that say, like here, erase your hard drive. It can also be a coding mistake that ends up doing something really bad on the worker side. So there's no protection for this right now. There are ways you can mitigate this. We say we isolate or sandbox workers, and you can run it in a virtual machine, which is one of the most secure ways you can do it. You can run it in a Linux container. It's less secure, but maybe it's good enough for your friends. And I encourage you to work on these important topics in R. I expect this to become more and more important. And I hope someone will come up with a framework to make this super easy to do, so we can use that in the peer-to-peer compute cluster. Thanks you for your attention. I encourage you to try it out. I encourage you to try the Futureverse out if you haven't tried it. We welcome feedback. It's a great community, and may the future be with you.